Спасибо. Я очень рад, что я сегодня могу быть здесь с вами. Я хотел сделать этот доклад на русском языке, но потом я понял, что я учил русский язык, когда еще не было Python. И я не знаю всех технических терминов. And that's the reason why I'm going to speak in English. So, I suppose all of you know some Python. Who has already heard of PyTables? Okay, a few of you. And who needs to store really large datasets? Okay. Large datasets means larger than your RAM. Okay. Why am I the person who can speak about it? I was born in Bratislava in Czechoslovakia. That entitles me to speak some Russian, but not really to work with Python. I have studied at the National Institute of Applied Sciences in Lyon in France. Came to Python from Java and Perl world about 10 years ago. And today I'm working as a software architect at the UBIMET company in Karlsruhe in Germany next to the French border. UBIMET, we do the weather, we sell the weather, and we are using Python to make the sun shine and the wind blow. I will explain later what that means. Usually at my work I import libs from Async.io world and Pandas ecosystem, and I enjoy really playing with Unicode and with time zones. But Unicode and time zones is not today's topic. We are going to speak about really large data. What we are going to use in our company, what sort of data are we generating? We are doing forecasts for solar and wind generators. Solar generators are simply the black panels on the rooftops all around the country, and the wind generators are the big turbines that are 60 up to 120, 150 meters tall. In Germany, the energy market is turning into the direction of this renewable energy forecasts. So there are about around 30,000 wind turbines generating at peak capacity of 50 gigawatts, and more than 1 million solar panels. But solar panels are smaller, they are on random rooftops, so it's not really relevant to talk about 1.6 million solar panels. But the total peak generation is also very important. So when we are doing this forecast for them, what we need other forecasts from weather models, and we need the measurement data. The measurement data comes from the generators themselves. So every time we know how much energy was produced by some turbine in the recent time, and also from weather stations. So the classical weather stations telling us the temperature, precipitation, wind speed, and so on. And we have our our meteorologists and physicists who need to have all this data on their machine to work with it, to find the ways how to forecast it even better. And also we need to send all this data to our other systems that use some machine learning or other algorithms to improve our forecasts. So it means that we need a place where a space or place or a sort of a data container that we can move freely between machines, and even to put it on a laptop, and our meteorologist can take it with him and work on it without a connection to our central servers. So we need a lot of data. How is this data organized? Usually the measurement data belongs to some domain and to a node. A node is a generator, weather station, or some measurement device somewhere in the power grid. Then we have some parameters and the time of measurement. This data gets updated. The devices or our suppliers, data suppliers, they send us corrected data later. But at every point we need to know what amount of data was available at that moment. So we really need to version it. And if we put everything into a central database and update it there and tell, okay, every time we can recover this data, we don't know when what was the status of this data at the given point in the history. For forecasts, it is the same amount of data multiplied by the time of calculation. So it means that if I measure the data yesterday at midnight, it was one given point. But if I do a forecast, every hour I do a forecast for the following X hours. And it looks like a cascade or like a staircase. So it's one forecast, next forecast, next forecast, next forecast. And for each time point in the history, I have several versions of forecasts. So I have to get a possibility to version them. What do I have as a possibility to store this data? If it is in the memory, of course, in Python, we can use dict of pandas data frames. It works well as long as all this data fits into your memory. But if you have much more data, you have to put them on the hard drive. So you can organize a directory structure, deep and wide, with some files at the end. CSV file is very nice in the Unix philosophy because it's just a text that you can read and write with any text tools, standard tools. But it's not really very fast to read and to interpret. A pickle of Python objects is a good idea as long as you don't work on the data and you don't want to recover the same data after a few years and after a few versions of pandas. So who already stored some pandas data frames in a pickle with version 0.8 and tried to read it with the version 18 knows what I'm talking about. JSON is very verbatim, so it writes a lot of bytes and has also to be parsed at once. And who is using XML today? Writing into PostgreSQL table is a good idea if you have measurement data, of course, because the measurement data, if you update it sometime, you can always recover the truth that is in the database. But for forecasts that you usually generate big amount of data every hour, and then what you want to do from the database is to read exactly this same block and then delete it after a few days. It doesn't really make sense to put it into a database where you have millions of lines that are always worked on as chunks. So HDF5 to the rescue. What it is? Hierarchical data format comes from the HDF group, a non-profit organization that works on it since many years. The current version 5 is online since over 20 years. So it's really an open standard that is freely available to everyone to implement. It is self-describing. So it means if you get a file, you don't need any interpreting help for it. You can really read and get the whole information that is contained in it. It is portable, so it means if you read and write it on different systems, it describes what is the endianness, so it means how the floats and multi-byte numbers are stored in it, in which order. It is hierarchy, so it is something like a directory tree, wide and deep, with datasets or with files at as the leaves. The tree structure is fully POSIX, so you work with it like with directory tree on a Unix system, and it supports even symbolical and hard links. So if you open an HDF file, you really feel like if you are working on your hard drive partition. It supports so datasets and attributes. So every node, every directory, and every file can get any number of attributes that can describe the more information that you need about your data. HDF5 is used in many sectors of science and technology. So NASA is using it to store images from the satellites. In meteorology, what we are using it is also the standard format NetCDF4. It is directly based on it, and also in other physics, finances, engineering, and so on. What possibilities do we have to interact with HDF5 in Python? In other languages, in most other languages, Java, C, and so on, there are libraries to access HDF5. In Python, we have two possibilities. H5Py is the low level. It tries to interpret directly one-to-one the functions of the C library, HDF5, and PyTables is the high level that we are going to have a look at today. It looks then like if you are working more with a database. So it is really high level. You can define more naturally the actions you want to do with your data. The current stack of H5Py and PyTables is next to each other. So we have HDF5 and then you have H5Py or PyTables and maybe pandas on the top of PyTables. But the new stack that, as I've read on the blog, they are trying to put it just as one stack. So the HDF5 C library, then the low-level H5Py, PyTables, pandas, and your user code. So PyTables is a package created 2002 by Francesc Altet. I've met this, I think he's Catalan, this guy, 3 years ago at the EuroPython in Bilbao. We had a very nice chat and he explained each other the possibilities of PyTables, and I also show him how we are using PyTables in our company. So it was also interesting for him to get feedback on how you can use PyTables for which interesting projects. And you are also invited to participate and to contribute to this project on GitHub. At the beginning, there were two versions, Standard and Pro. The Pro version was used to get some money for the development, but now it is entirely sponsored by NumFocus, and everything is open source. The Pro version supported a few more functions that are now available for free, and we are going to look at them. The PyTables has the hierarchy, this directory structure, and at the end you have NumPy arrays or the tables with arrays. It is fast. In PyTables it supports indexing, so you can index whole columns and then read the data really quickly. And it is also optimized for the size using different filters that allow you to store the data in compressed form on the hard drive. For example, BLOSK, developed by Francesc Altet, that is a really fast way to store data in a compressed data format on your hard drive. It supports mathematical operations thanks to the NumExpr library. It is, of course, file-based, self-contained, NDNS. These are the attributes of HDF5. It's beautifully Pythonic, and you write once, and if you write your data once and read it many times, it may be really useful to use PyTables. How do you install it? It's available in all standard systems, even in Conda. You import it as a tables, but the package name is the PyTables. The dependencies, the low-level H5Py is based on only on NumPy, but the PyTables has NumExpr and BLOSK for accessing or reading data using NumExpr expressions, and BLOSK for the compression. So as I told, we import it with tables and then open the file and close it at the end, but I recommend the second way with context manager. So it means that in the block, in the indented block, the file is open and then it will be closed automatically. The A attribute, there are several attributes or ways of opening the file, append, write. So it means that you can, using this, you can prevent accidental overwriting of a file on your drive. The tree structure with create groups. Groups are like directories. You can create the directories with names or based on other directories. And then below them create, this is just a placeholder, different nodes. Or you can create the nodes directly and create parents. So it feels really like make dir in Unix. Accessing the datasets, you access them like directly like path or below the directory, and this is very nice by PyTables. It has also natural naming, so your file object .root, and then you can access the names of the groups and nodes below using dot notation, and even in IPython it works with code completion with tab. The dataset types array is just like any NumPy arrays, any NumPy array with any number of dimensions. C array is chunked and compressible. E array extensible in any direction. Variable length, and table is the most interesting. It looks like, it feels like a database table. The supported data types, the standard as you are used in NumPy or in Pandas. With time, it supports only integer 32 or float 64. This is Unix timestamp in seconds since epoch, and this is also seconds since epoch, but it allows you to use time units below 1 second. Enum string, so you can write in Unicode all the data you need. If you create an array, you say where to write it, the name of the array, then directly the object in the number of dimensions, and the type of the data you want to store. So this means that this creates directly the array, and then you can access it as you need. The chunks and filters. Chunks means if you have a NumPy array, it is block that has to be read and written at once. Chunks allow you to section it into regular shapes and then read or write only the shapes you need. So these are like predefined tiles. You have to choose the right size. You can define which size you want. If you take too small of them, it has to index all of them. So behind all these small parts, you have a big B tree that has to find all these elements. And if you have very small chunks and you want to read or write more data, it has to read more chunks, and it may take a longer time. If you create too large chunks, it will have to read and write always a lot of data. So it's really worth playing and trying to find the right chunk size for your data. And each chunk can be then filtered. With a filter, can be stored on the hard drive in a compressed form. So for example, here we take the library BLOSC with the highest compression. Shuffle means that it turns the numbers the way that the bytes of floats are stored in a different way. And Fletcher 32 is a checksum, just to make sure that your data has been written correctly. And then you create the array. And here we decide, we take the chunkscape 100, and with the filters, and then it will store the data on the hard drive in a smaller way. Now we can make a test. We take an array 1000 by 1000. These are just 4 objects, zeros. This is arranged, so numbers 0, 1, 2 up to 1000. Sinus of them, and totally random numbers. So we have 4 objects, and we are going to see how we can store them. The filters is no compression, standard zlib compression, and BLOSC compression, and we take 3 different sizes of our chunks. Oh, I'm sorry for that. The table looked well a half an hour ago. Now it doesn't look so well. I can those who are interested, I can show it afterwards. Means that if you have compressed data and it's regular data, it will be quickly stored on your hard drive, and the file will be much smaller. Yeah, sorry for that. So you have to measure and don't guess. E-array is an array that allows you to extend your data in one direction, so you can append to your array later more data. And table, it is what is interesting. Here is the definition of the table. We are going to look at that. And then you can define if you have some size that you expect. And PyTable is going to try to optimize the chunk shape and chunk size for you. So the table description, it looks like create table in database. You can define it with a dictionary or with a class definition. Our table will have three columns. And then we are going to read a random data I found on my hard drive. It is the measurement, weather measurement for Minsk for the past 2 years. This way we define the table, define the filters, and we open the file and then create table. When we print this tab object, we will see that it is the content or how the table looks like, and then we can write into it. You iterate over your data frame, and then Pythonically you write to your row object and then append it. Or you can do it quicker, faster with list comprehension. The attributes, so our table can have some attributes. We can just write whatever we want. The attributes will be, I suppose we have, how can I reload the Control R? Yeah. Yeah. Okay, it wasn't reloaded. So this is before this table with the times and the sizes of our of the test we did before. Just quickly to show you that if we use a BLOSK, it will be written much faster than with other library, and also the size will be smaller. If you write or read on your hard drive compressed data, your processor is faster than your hard drive when it is reading or writing. So it's now it's a good idea to communicate with the hard drive in a compressed way, and then in your memory decompress and compress it in your memory. Okay. Yeah. Okay. So we wrote it. These are the attributes, and then I can read the table. Just access it like a NumPy array. I get the data, or I can access individual columns. So this is just a column with the temperature. Or we can also use NumExpert and tell him we want just some data. So these are all the, not the days, but all 6 hours block where the temperature in Minsk was below -20 in the past 2 years. Or on the other way, where it was exceptionally hot here. Yeah. Okay, so the tools in Shell, if you install PyTables, it will come with a few tools that you can access from the command line. It is ptdump that can write the content, the structure of the data. If you add -d, it will write even the whole content as a CSV file, so you can visualize it. Ptree, it's some information on prints some information on how the data is compressed, and also the directory structure as a tree. The Ptree is very interesting. If you write into a file and you update or delete nodes, it will not recover the space. So Ptree is sometimes a good idea just to take a file you have and then convert it into a new file, taking just the data, just the nodes that are still active. Also, if you change something in the structure, then just throw it through Ptree. It will purge deleted data, and you can also repack the data using a different compression filter. Ptree can be also used to merge your directory structures. So for example, if we at our company, we have a lot of data that could be written in one PyTables file with a very precisely defined directory structure, we can also split it into individual files and still keep the subdirectories. So afterwards, if we say, okay, we need now from this file this part, this part, this part, this part, we can merge them, all of them, into one file, and we can use Ptree for that. It's a good idea if you have a lot of data that you structure and your namespace, and you try to keep the right data under the right name in a directory structure that has, for example, 4 or 5 levels. What is very practical if you are using Z shell, is defining global alias. This alias -s in your Z shell RC file means that if you, in the command line, you execute a file with extension h5, it will start this function, and this function will start IPython, import tables, and read the file. So if I do something like this, it will tell me, okay, your h5f file is this one, and then I can access or read the data in IPython. This without giving the executable file attribute to h5. So it's practical if you have like PDF, you can start Zatura or .py or Python program can start your Vim editor, or I don't know what other editor could someone use. Another tool that I have not here is VI-tables. It's a graphical interface that you can use to browse an H5 file with a directory tree structure and visualizing the tables. If you want to parallelize, reading is not a problem. It's a file, so any number of processes can parallelly read. Writing is a problem. It's not a database. You can use a single writing process. You can lock the file. You can use async I/O with a web service. And also, if you write a file, it is probably not a good idea to read it at the same time, because it's possible that some bytes in the background are going to be changed. The former Pro version and now the whole version, every version of PyTables supports indexing. So you can create an index on a specific column and then also remove it. It will allow you to read the data, to access the data in a selection much faster. No real support for transactions, sorry. And there is a undo and redo function on structures. It means if you create new groups or nodes, you can, at the beginning, you enable the undo, and then you can mark anonymously or with a concrete name, and then you can jump back to a special mark that you did. Since PyTables doesn't release the space, your data will stay in the file, and if you just undo the creation of this data, it will just mark it as non-accessible. But you could also jump forward to redo this step. There is only a single line of marks, so you cannot really branch with it. So, at the end, how to store large datasets if you need hierarchy, fast write and read, compress, so small size, resizable datasets, and you are working already with NumPy or Pandas, and you need self-contained data format, and you want to work Pythonically, just import tables. Thank you very much.
Okay, questions?
Hi, thanks for the talk. Well, as far as I understand, a single node in this file cannot exceed the amount of RAM you have, right? So if you access it,
it can.
So how does it work in this sense?
You can access, if a node is larger, you can access, you want just the lines that are you do something like a select on a database. You say, give me all lines where this column is larger, smaller than something. And I'll show it. There are, yeah, look here, tab where. It's a generator. So I just, I can get any size of, any number of rows back because I'm just consuming one after another. So you can work really with any number of data. I can tell you the limit on the number of rows in a table is 2 to the power to 63. So how much is it? You will have sooner problems with your file system than with PyTables. It supports really absolutely large data. We have data the files of several hundreds of gigabytes, but a terabyte is not a problem.
So it's smart enough not to load all the table.
Yeah, you don't really. Yeah, that's made for it because it's really for a lot of data, a lot of data sets.
Right.
Yeah.
Thank you.
Thanks. Thank you for the report. That's a nice thing to know. But there are too many good things said about PyTables and HDF5. Are there any bad things you can tell us before we fall into this? And maybe it's vulnerable to data corruption or something. So you must care about these. Don't forget about that. Some practices.
Writing is the problem. So we are strictly using always one process that is writing in it, and we pay attention that there are no concurrent writes. Otherwise, it works. So you can. It depends if you use it as a database, so a static file that is always there, and you just add things. It is a good idea to petty repack it from time to time. But also we are using it as a message format. So I create some file and I send it somewhere, and I won't change it again. I will just read it afterwards. So for that, it's also very, very suitable.
So this means that your recommendation is that only one client works while writing, and I assume reading too.
Reading
while I write, can you read?
There must be only one process that writes at the same time. But if you create the data once and you use it afterwards just for reading, you can have any number of processes that read it at the same time. If you have a data that is already finished and nobody is going to write into it. Yeah.
Thanks.
Thank you for the presentation. I guess there must be other options for this sort of task. So can you list a few of them and tell about their benefits and, or downsides in comparison with PyTables in particular? So, not Python at all, maybe.
You mean this?
I mean the whole, the whole stack maybe. So with this, so there's no integration into what an engineer uses on a daily basis. Like data frames in Pandas or Spark or something. So I guess it's part of that, but as a whole solution. So something packed that one uses unless they use PyTables and maybe HDF5. So
the question?
What are other options in terms of the whole stack?
Other options. So instead of PyTables, no, of course, next to PyTables we use data frames and also the Pandas ecosystem. We are still not in need of Dask or other possibilities to work really on more machines. So we are not that far. But this PyTables, we are using it since 7 or 8 years. And there are also parts of code that are that old and that simply work. In such a huge system, it is not so easy to change any part so quickly. So the PyTables is a format that didn't change since so many years. And it allows us even to read older files from that time. Of course, now if you have a newer version of data frames, of pandas, having, as I told before, having a pickled data frame on your hard drive that is 6 years old, you're not going to be able to read it again. So.
Thank you.
Question.
Hello, thank
Hey.
you for your presentation. I would like to ask you, where usually are you running your statistical programs or calculations? Like you have data on the some, I think, remote server, maybe, or usually you need to, or how you need to download it, this data, or and run it locally, or you have like some access or some smart way to how to run statistics, for example, like periodic statistics. If you said you calculating usually per day or per some time,
Yeah.
how it usually works?
The data is on the server and the calculation is done there. This is just if we exchange the data with other networks or with, or if our colleagues need to work with them on their computer, they just download a small part of the data, put it into PyTables data, and they know. What is interesting is that you have a H5, a PyTables file, and then you can just name it some way, and then you can put it somewhere into configuration data and tell configuration file, and then tell, okay, I worked with this file, and it is like a snapshot of the history of the current status of forecasts and measurements data that we have, and you can always come back to it and tell, okay, we calculated some forecast based on this data.
Do you using some kind of like Jupyter notebooks, like Jupyter, sorry,
Yeah.
like Jupyter notebooks directly on server, like directly on remote server?
No, not on remote server. It's local. Yeah.
Okay, and what about like language? In relational databases, you usually use the relations like tables, and you usually use joins.
Yeah.
That's
a good question.
I think it's like you said, NumPy arrays are good, but you need to use joins, or relational database was created because you need to use joins.
This is not normalized database. So usually in PyTables you denormalize it to be able to access every table separately. PyTables doesn't support joins. It's not database.
And if you want like to join two tables, you need to read two files and join it manually.
Yeah. That's not done for not done to work like a database. Okay. We have databases for that.
It's like I know about timescale DB or some like databases that was created directly for this purpose, and now it was good to know about some.
What's beautiful about PyTables, you have one file that you can read, write, and you don't have it somewhere in var lib PostgreSQL. You have it where you need it, and you can send it around.
It has, okay. Yeah. Thank you.
I think there will be the last question because we have timing.
If you want to run some analytical queries, like for example, calculate average of one column with some filtering applied, like where some field equals some. Okay, so how the performance of PyTables will compare to columnar storage like Vertica, for example, single node of Vertica, if I load all the data into it. Will it be comparable? Will you recommend for this kind of operation?
No, I'm not able to answer this question. I don't know. I don't know the number. I have not tried it, real analytics. Sorry.
I think that's it.
I'm around until tomorrow, today, so if you have more.